I guess we'll get rolling here. I just want to thank everyone for joining today for the first Conservation Sciences seminar of the spring 2022 semester. We're very fortunate to have Dr. Lynn Waterhouse, the Assistant Unit Leader with USGS Minnesota Cooperative Fish and Wildlife Research Unit. Dr. Waterhouse joined the Minnesota Cooperative Fish and Wildlife Research Unit as Assistant Unit Leader Fisheries in summer of 2021 at the University of Minnesota. Dr. Waterhouse's research focuses on quantitative fisheries stock assessment with the aim of providing relevant and timely information to management agencies with the goal of keeping populations sustainable or restoring endangered populations. She's a member of the Grouper Moon research team studying the largest remaining spawning aggregation of Nassau grouper in the Caribbean, located in the Cayman Islands. Waterhouse holds a master's degree in statistics from Pennsylvania State University, which has led to several interesting collaborations, from assessing damselfish calls in American Samoa to assessing the performance of medical ventilator in a hyperbaric chamber. Prior to coming to Minnesota, Dr. Waterhouse worked at the John G. Shedd Aquarium in Chicago, with the focus of her research in the Bahamas, which sounds very nice right now. Dr. Waterhouse enjoys spending time below the water, but we'll definitely have an adjustment getting used to the frigid waters of Minnesota. So I guess just before Dr. Waterhouse gets started, I just want to let you know any questions that you might have during the course of the seminar, please feel free to put them into the chat box and we can get to those during the Q&A. We should have maybe 10 or 15 minutes at the end of the seminar for questions and answers. So if you feel like unmuting and just asking a question directly, that's great. Otherwise, we'll get to them in the chat box. So yeah, I'll hand it off to you, Dr. Waterhouse. Thanks for joining us. We appreciate it.
Thank you. And thanks for that introduction. All right, so I'm going to talk about two different quantitative models today that were applied to missing data. So that's the learning something from nothing. And do you see my slides? Okay. So before I begin, I just wanted to tell you a little bit about the Cooperative Research Unit in case you're not familiar with that term. There's one at Minnesota. They're all over the United States in 38 different states, 40 total units. They're actually currently hiring, so a plug for that. If you can't find the link, but I can direct you to it, it's on USA Jobs or on the Co-op Unit website. You can find them for both Montana and Utah. They also frequently hire postdocs. So for the Minnesota Cooperative Fish and Wildlife Research Unit, we are focused on graduate education and doing research with our cooperators in mind, and they are USGS, University of Minnesota, the Minnesota Department of Natural Resources, the Wildlife Management Institute, and U.S. Fish and Wildlife Service. And there's 4 of us here at the university, the unit leader, David Anderson, the other assistant unit leader, David Fulton, and then myself, along with our program/project specialist, Hattie Saloka, along with a bunch of postdocs and graduate students. So a little bit about me, which you heard of, but I went to undergrad in Ohio. And then I did an REU in the summer in Alaska, and that's where I learned how cool it was to combine fieldwork plus math. And just a plug, if there is anyone that is an undergraduate listening to this, or anyone that works with undergraduates, remind them that right now is the open season for those National Science Foundation research experience for undergrads. They're paid summer programs, and they're due very, very soon to apply for them. But it's a fantastic way to try out science. And they're in a variety of fields, including some of the social sciences. The next summer, I went to Hawaii and got to work on boats. And again, discovered I still love doing this. So I headed off to grad school at Virginia Institute of Marine Sciences. And there I thought I started what was going to be a PhD project that didn't work out at all. So it became a master's project. And then I headed to Penn State to do statistics. And this has really shaped my career and helped me open doors to a lot of really cool things. But after that, I had to return to the coast in marine biology, going to Scripps Institution of Oceanography. And then I headed off to Shedd Aquarium until I came here. And I've worked on a variety of different species, both in the tropics and in colder waters, including salmon. But we all know that fisheries data is really messy to work with. So there's a variety of problems that you have with fisheries data, from the fact that there's irregular sampling, they've changed gears through time, funding constraints can have an impact on what the data looks like, natural disasters mess it up. Any of us analyzing time series data are going to have a fun time handling what happened in 2020 with our data sets, with COVID impacts on sampling. Sometimes there's a lack of sampling design. It was just kind of willy-nilly, grab what you can, not realizing how it would be analyzed in the future. And then there's also lost, missing metadata or the data themselves. And that's the problem I'm going to talk about today. So when you have missing data in a data set, there's kind of two major ways that you can deal with it. You can either remove those missing data points, or you can impute the missing values. So when you remove the missing data points, that's super simple, really easy to do. It does cause some problems though, in that a lot of models can no longer be used when you have these gaps. So it might violate the assumptions of those models. So it's not always something that we want to move forward with. When you impute missing data, it might increase the availability of models that you have to fit to the data, which is nice. There's a lot of options on how to impute missing data. Anything from something simple where you just take the mean or the median or the mode of values around it and fill them in. But there's implications of what option you choose in terms of the independent structure to the data and correlation for how you fill in those missing data. So I'm going to talk specifically about two Bayesian applications of imputing missing data. The first one, calling it imputation of data, might be a little bit of a stretch, but it's leveraging the design of a system and multiple observations to kind of fill in some missing information. And the second one is a Bayesian-like model where you actually do impute missing data with growth rings of tropical tuna species. So first, I'm going to talk to you about Steelhead. So Steelhead, like other salmonids on the Pacific West Coast, it's been a sad story through them through time. This just shows survival rates for Steelhead and Chinook. They've been declining since the 70s from a combination of anthropogenic impacts, climate change, fishing, a tough road for them. Steelhead are anadromous, so they migrate upriver from the ocean to spawn, max age of 11 years, max weight 20 kilos. There are some ones that live solely in freshwater and some that spawn twice, but I'm going to talk about your average steelhead, so the ones that come up and spawn one time. Steelhead are very important to the salmon culture of the Pacific Northwest tribes, along with large commercial and recreational fisheries and the ecosystem out in the Pacific Northwest. Unfortunately, one of those things that have impacted these species are anthropogenic impacts on the riverine systems. So this map is in Washington and it's the location of dams on the river system. So you can see it's highly impacted, which has resulted in steelhead and other salmon populations not doing too hot. And so this is the status of steelhead over on the west coast of the US, where the red population, so down in Southern California, they're endangered. And then orange is threatened, yellow, concerned, green is least concerned. And what you can see is there's very few left that are least concerned. Everything's kind of orange and red. It's not doing that hot. And when things get listed, we have to manage them and assess how they're doing. And when you try to assess and manage salmonids and steelhead, it's much easier to manage them when they're in the river than out in the ocean. The ocean's much harder to control, often much harder to study and assess their numbers. And in fact, the hydroelectric companies, which out in the Columbia River Basin is the Bonneville Power Administration, they spend millions of dollars to the tune of $600 million in 2020 doing work towards fisheries and wildlife, which includes things like habitat restoration, fish monitoring, hatcheries, managing predators, moving fish around. So this is a lot of money. And obviously when you're spending this amount of money, you want to know how is it effective? Is there a better way to do it? And this ties in also with species that are listed by ESA. You have to know how are they doing as well. So there's a big need for information on these species. And like I said, it's easier to manage them in the river systems, but rivers are really spatially complex and quite large out there. So how is it that we figure out how many salmon are going through the river? A common way is to count fish at dam or weir passages, which is a really time-intensive method to do this. It used to involve a person sitting in front of the dam window with a clicker or computer system actually counting the fish. So you can also imagine this was then limited by light, limited by shifts. Now there's some fancier technological ways that they do this, but it still has limitations. They can also go out and do red counts where you count the red or egg packets in the stream as you walk. They're very visible, especially in the shallower sections of stream where they spawn. And then you can relate reds back to a proxy of adult abundance. But another technological innovation is we can use PIT tags. So if you're not familiar with PIT tags, it stands for Passive Integrated Transponder. It's very similar to the technology that would go in your race bib if you've ever run a race before, that it knows when you cross the start line and when you cross the finish line. So they're really tiny and they've been used since the 1980s. They're very low cost, long lasting. You implant it in the fish. Here's a PIT tag in somebody's hand, so very small. And how they work is you stick your PIT tag in the fish. And these are arrays here in the water that you see, the things that looks like an underwater ladder. So as your fish swims past the detection array, hopefully it's detected by both of them. And the PIT tag has a unique code, so you know exactly which fish swam by your array. And in the Columbia River Basin since 1987, over 51 million fish have been PIT tagged. This is tracked by the group PTAGUS. And in 2020, they tagged 1.75 million fish as well. So lots of fish, lots of data. PIT tags also have some difficulties in that they're messy data. So river systems are complicated, as I said. It can become a big data problem when you have millions of tags going through your system. You also have missing detection. So those detection arrays, in that prior picture, that was a really nice shallow section of river. So the fish would always pass really close to the array, but rivers flux and the water height increases. So you're further away from the array. You might not be detected. Storm systems can knock out the arrays. It used to be a problem too, that if people had certain types of radios in the vicinity, it could interfere with the array. So lots of ways in which array detection goes down. It's not perfect. It used to also be the case if two fish passed at exactly the same time, that the tag signals could interfere with one another. So here is where it becomes a missing data problem. So this is a really simple cartoon of a river in blue, and you've got your detection arrays. Here we have 6 possible detection arrays. And you can imagine your fish swims upstream, goes through the whole river. There's a variety of detection histories you could get, but in the extreme, it could either be detected everywhere, so you get a bunch of 1s, or not detected everywhere, but it still went, and you get a bunch of 0s. So this is where it's a missing data problem, because these detection histories could represent the exact same movement, and it's really hard to tell from them that that's what's going on there. So looking at it a little closer, we have our river, we have a detection array. This one has a probability of detecting the fish of 0.5. So that means when your fish passes the array, you've got a 0.5 probability that you'll detect it, 0.5 probability it's undetected. But we usually don't know these detection probabilities. So instead you have your fish that passes by, and all you're left with is this detection history of 0, where it wasn't detected. So you don't know that it actually went upstream. If you knew somehow that it passed the array, so if you had a net further upstream so that you were catching all your fish in, you would know that it passed. So your array detection in this case is 0% with that one fish. So what we actually do is we leverage the history of multiple fish in order to figure out this array detection. So now we've used our net to catch 8 fish upstream. And of these 8 fish, the green ones, so 6 of them, our array heard. The 2 red ones, the array did not detect. So now the array detection is 75%. And that's not all that matters, though, in terms of how fish are moving. We also have what's the movement history of these fish in the system. And if we had a net lower down in the river system, we had caught 2 additional fish. So now we know that 2 fish didn't pass our array, 8 did. So the movement history is that 80% of them passed by. So now we have our detection history of 0, and we want to know, did the fish pass? And if we have this other information, that our array detection is 75% and our movement history is 80%, we can back calculate what's the probability that this fish went up. So here's all of our probabilities. Also in this type of work, it's assumed that there's no false detections. So the probability that the fish moved upstream if it was detected is 1. And the probability that it's downstream if it's detected is 0. So now, with a history of 0, the probability that it went upstream is going to be 0.5, and the probability that it was downstream if not detected is 0.5. So these are those red fish visually. So typically how people analyze this type of data is you can use a Jolly-Sieber method. There's also maximum likelihood approaches. A lot of them developed by Skalski. But with a large river system, the maximum likelihood approaches wind up with an enormous likelihood that can be really complicated to calculate. That's why shifting to Bayesian methods can be really useful. There's less calculations. And so this Bayesian model allows you to estimate the proportion of fish moving to particular sections of the river along with the detection histories. And we do this by leveraging all of those upstream detections from other fish to figure out what a fish with a history of 0 is really doing. And it's also more common in a river system that you would have a double array rather than just a single array like I was showing before. So now the probability that a fish is detected at all when it swims by, if individual arrays have detections of 0.75, it increases because the possible detection histories that let you know it swam by here are going to be 0, 1, 1, 0, and 1, 1, where 1, 1 would be it's heard at the first and second array. So now your probability that the fish is detected at all is 0.9375 if you assume these arrays are independent. So what does a detection history look like in a more complicated river system instead of just a linear system? So we have a fish has entered the system, so it gets a 1, and then it moves on up to branch A. It's not detected though, so there's a 0 there, but then it moves on up to branch B and it is detected. And then it stays put. So we fill in the rest of the detection history with zeros. But for a fish that wound up here, it could have a variety of individual detection histories. This is just one example. Some of the other detection histories that wind up in the exact same place are shown here. So we're going to leverage all of these different detection histories in order to determine what the probabilities of movement are, along with the probabilities of detection. The real system's even more complicated than that little schematic. So this is the Upper Columbia River Basin. It has 3 main subsystems: the Wenatchee, the Entiat, and then the Wells. When we turn that map into a model schematic where each of these circles represents a place where there's a detection array, this is what it looks like. The entrance to the system is PRA, that's Priest Rapids Dam, which has some downstream places that flow into it. And then you can go into the separate parts of the system. Green is Wenatchee, purple is Entiat, and then the orange and yellow represent the wells. And to go from probability of fish winding up in places, because that's not really what management cares about, they want to know numbers. So you can turn probabilities into numbers by knowing how many fish enter your system. So getting an estimate of fish passage at Priest Rapids Dam. And that's where more standard methods are used. So at Priest Rapids Dam, they have people doing dam counts. And in 2016, they estimated that just under 14,000 fish passed Priest Rapids Dam. So that number was used to fill in fish throughout the rest of the system. And this model was validated by taking another dam in the system, Tumwater, here in the Wenatchee, where they once again counted fish. So the Washington Department of Fish and Wildlife estimated fish passage at Tumwater, and they counted just over 1,300 fish using trap and video data in a given year. And when we applied our model to the data, which this model, it can be applied to hatchery and natural fish separately if you believe they're doing something slightly different, or if you're interested in treating them as different populations, which the management did want to keep hatchery fish and natural ones separately. So we have the hatchery fish estimate shown here, just under 650, and the natural population here in blue, just over 500, which gives us an end estimate that has a 95% Bayesian credible interval that includes the true number of 1,300, which was great because this shows that the model worked. So that's fantastic, and the model is validated. And this model is actually used to assess Chinook and Steelhead populations in the Upper Columbia River Basin by the Washington Department of Fish and Wildlife. So through time, they're estimating what Steelhead are doing. And again, they like to keep the wild and hatchery populations separate. And I was talking before about all the money that's poured into monitoring salmon populations in the Pacific Northwest. There's lots of money, lots of salmon to assess, and they're always looking for ways to better spend their money. And so one of the great things about a Bayesian model is that you can also then turn it into a simulation framework to look at changing your assessment system, specifically looking at changing tagging rates. So how much better is it if you tag more fish versus how does the model act when you change the system? So we can change the detection array efficiency. So here's your Toy River. We can look at adding another branch into the system with some arrays, if that's an area of importance. You can look at adding additional arrays, which I'm going to focus on. So this is one where it went from a single array to a double array. And there is a specific problem with a single array where these zero detection histories, when you have a lack of data, it can get you into an unfortunate problem. So now if we envision in this toy example that branch A is a single array. So right here, there's just one detection array. So the fish that stay just below branch A or move on past branch A and stay put, they're going to be confounded with one another if we have imprecise detections. That is, if we have a lot of zeros here and a lot of fish stay either right above or right below, we have a lot of zeros with no more information that can help us figure out these detection arrays, because the fish haven't moved any further to let additional detections help us determine the probability here. So if you have a detection history of 1, 0, so it's in the system, but then it was not heard at branch A, the fish could either have stayed below or gone up above and not been detected. And if the majority of the fish stay this low in the river, you don't get anything further up. So again, we're not going to be able to figure out the detection probability here. And there's really no way around it other than adding a second array into the system. So this isn't so much a modeling solution to missing data, but an actual technical one in that you have to add another array. And so just an example of how much better you do in simulations. So here, the light plots are when you have 1,000 fish in your system, and the darker color box plot is with 10,000 fish. So obviously more fish gives you a more precise estimate of passage. Sorry about that. My PowerPoint decided to shut down. Sorry about that. But what that plot was showing is that if you tag more fish, you get more precise estimates. Nothing really newsworthy there. You could have figured that out. But also having a double array versus a single array really helps out. Okay.
It wouldn't be a good Zoom seminar without some technical difficulty. So this is good.
All right. So again, gray box plot's 10,000 tagged fish. White box plot is 1,000. Over here on the right, we have when you have a single array at that A point. So we can see our percent error is around 1%. And over on the left is when you have a double array. So when you go from having a single array to a double array, it actually almost completely eliminates the bias from the system. So really in this case, where you have lots of fish staying low in your system, so there's not a lot of upstream information you can leverage for them, your only solution to get around this issue of zeros and possible missing data is to add in another array. And this type of model will work for any fish or creature that moves through a branching system in a one-way directional movement. So there's lots of other salmonid stocks that this can be applied to. It can be extended to other river systems. A big limitation of this type of model is it's a one-way trip. The nitty-gritty of how the modeling is done doesn't work for fish that fall back. This is just when you're interested in a one-way trip through the system. So you do have to clean up the data prior to putting it in. And it's relatively computationally intensive, depending on how many tagged fish you have and how big your network system is. But it allows you to estimate these probabilities of returning to specific sections of the stream along with the detection array probabilities before, and it is in fact used to assess steelhead and Chinook stocks in the Pacific Northwest, along with it could be used in a simulation framework to decide how to spend your money. Should you tag more fish? Should you add more arrays? So shifting gears now to talk about tropical tuna and how we can use imputation to aid us in growth studies of tunas. So there's some standard methods for aging fish, which include using a variety of hard parts and soft parts, and you can also do tagging. Many of these methods wind up being possibly lethal, have high extractive costs. Things like scales and fin spines tend to be non-lethal, really quick. Commercial fisheries might like them a little bit better since they're non-lethal, so it doesn't affect the market value of the fish. But an issue in using fin spines and rays is that for many fish, they have vascularization in the core. So this occurs in tunas, but also freshwater fish like suckers, trout, and catfish. And the zone of vascularization in the core of the spine can expand with growth, erasing the earliest growth rings. So what this looks like, and this is a yellowfin tuna spine. So this is sliced through the spine, and this zone labeled DV is the vascularized region. So it's obscuring any rings in there. So if this is a really young fish, so there's no rings in there, you could imagine that the diameter of the spine shown with the green line, and then we get an older spine of a fish now, and the vascularized region's even bigger. And if we compare the size of that first spine to this vascularized region in this larger spine, you see that the entire first spine is now obscured in this bigger spine. So any rings in this section will be gone. So this is problematic because we'd like to use spines because they're cheap, easy to get from fish, or easier than an otolith where you have to kill the fish. You can at least release them once you've taken a spine. And so ways that people have dealt with this in the past is you can just assume the rings that you count are the true age, which is the naive thing to do. And then a variety of methods have been come up in the past where people would try to apply regression methods or you would get representative samples of each age and you would know what size the spine is and then kind of manually assign each spine to a number of missing rings, but really hands-on intensive. And K-means cluster analysis was done as well, although you have to know how many ages are in your sample to get that to work, which in fisheries, we often don't know the true ages of our sample. So the method that we came up with was a Bayesian-like imputation, and I'll explain why it's Bayesian-like and not strictly Bayes later on. But I'm going to compare the Bayesian method with the naive method today. So the Bayesian model, we named it Germ, or growth estimation with some rings missing. So your goal is to come up with the number of rings that were in the inner part of the spine, so that rings inner, in order to get true age. Where your rings inner is either 0 and no rings are missing, or not available because there's vascularization and you're not sure what's going on. In the simplest case, we assumed that the spine width follows von Bertalanffy growth curve. This would be if the fish growth followed the von Bertalanffy growth curve. And now the number of rings in that inner section of the spine can be modeled up as a Poisson with mean mu sub v, where mean mu sub v is the mean number of rings that would be in a vascularized region for a fish of spine width v. And we can invert this to calculate what's missing. And it requires very little data. So you just need to know how many rings do you see? Do you think rings are missing or not? And this can be NA if you're not sure. What is the overall spine width? And what is the region of the vascularized section of your spine? So this is the model itself again, but the number of missing rings comes from a Poisson around that mu sub v, which is given by this equation here. And it's just the von Bertalanffy growth equation inverted. So why is this Bayesian-like instead of Bayesian? The priors are not purely hierarchical for this model. So this specific model is more similar to the type of Bayesian work that you would see in data science, where prediction is what you care most about, not having a pure Bayesian model that represents what's going on. And it's to avoid a circular logic node. But it turns out it works really, really well. And we've looked at it using simulated data and Yellowfin tuna, but skipjack. I'm actually going to talk about the skipjack data today, not the Yellowfin data. So this is how it does in simulation. So this is a big table. You don't need to read the numbers. I've color coded it. So this is the naive model. So green means it got it right. Yellow is off by 1, orange is off by 2. Where the rows are the true age of the fish and the columns are the naive model prediction for age of the fish, which in this case is just the count of the observed rings. And what you can see is that as the true age of the fish gets beyond 2, the naive model does pretty poorly. And that's because rings have become vascularized. So you're not counting the true age of the fish. So you get more yellow and more orange. The germ model, on the other hand, it does really well. So again, green was when it gets it right. So it gets it right all the way up through age 10 fish. Yellow is off by 1. So it does predict some fish are either a year older or a year younger. And so the germ model does better. It gets it right more than 70% of the time. And it also does a better job of estimating the von Bertalanffy parameters from that equation, which is really important because if you're taking your von Bertalanffy equation and using it to come up with a mortality estimator, which is shown here at the bottom, where your total mortality comes using the Beverton-Holt mean length estimator, the naive model will actually overestimate your K, or your growth parameter from the von Bertalanffy curve, by 50%, which means that your estimate of mortality from this estimator is going to be 50% higher than it should be, which can have really big implications for your management of these stocks. Whereas the germ model prediction for your K, for your growth estimate. The 95% credible interval includes the true value, and it's pretty close in the median. And this is how the model looks with those simulated data. So you can see the naive model, it thinks all the fish are younger than it really is, so the curve's getting pushed towards the left. And how does this do with skipjack data? So this is skipjack data from the Atlantic Ocean, and the spines were collected by UFIRSA and AOTTP. So the first question is there evidence for vascularization? So this graph shows us the diameter of the first ring that you observe in the spine, and then the count of the observed rings are the colors as we move towards the top. So this orange violin plot on the bottom is when you see one ring on the fish, most of the diameters for that first ring tend to be around 2. And up here at the top in pink, we see 6 rings in the spine, and the diameter, the median tends to be closer to 3. So in fact, there is evidence that vascularization is obscuring some rings, perhaps as many as 2. If you squint at this, just looking at where do the medians of the first ring fall for these different observed ring counts. And when we apply the model to it, we get these different estimates. We don't know the truth to compare it against, so it's a little bit easier to look at it visually. So these dots here are the pairs of estimated age from the germ model along with the spine half width. So you could think of this as it's similar to your length and age curve that you'd see a von Bertalanffy curve through. The blue line is the germ model. So it's fitting nicely through the data. The naive model is assuming that the fish are younger, so the dots don't actually get pushed out this far in terms of age. So it's shooting off up really high through the data. In fact, the D-infinity or the asymptotic spine size is 5.41 from the naive model, which is not actually a data point that we have. It's 2.59 using the germ model, which is kind of within the higher ends of sizes. This data set, it turns out, is actually a little bit problematic. If you're looking at these curves and thinking to yourself, neither of those curves look really good, Lynn. I wouldn't be happy with them. I agree with you. This data set, it turns out, doesn't actually have enough representative old fish to truly capture the asymptotic spine size. And there also might be a problem with these youngest fish in that it was self-selecting due to gear selectivity or some other thing, fish that were large. This isn't a great example, but you could argue, given this data, that it's better to have an asymptotic result that falls within the bounds of your data, or this is just proof that you need to go get more data to try to apply the model. But in simulations, this model works. It's a flexible model. You could use something other than the von Bertalanffy for your growth curve, something like the Richards. And with simulated data, the model works well. Also, if 100% of your data is missing and you need to impute all of it. So if there's vascularization in every single one of your samples and you're not sure if all of them have missing rings, that's fine. The model would still work. And again, why this is helpful is it allows you to use data in a more efficient manner. The other methods that people have proposed for handling vascularization in spines have all been a little ad hoc and required some external knowledge. But it's really useful to enable people to use spines compared to some of the other methods for aging fish. Again, in that we could get larger samples from commercial fishermen who want to keep the fish whole and don't want to let you hack into it to grab the otolith, or from catch and release anglers. And again, it avoids that naive issue where you overestimate your K, your growth parameter from the von Bertalanffy, which would have you overestimating your total mortality Z if you're using the Beverton-Holt mean length estimator. So these are just two examples of how you can use a Bayesian model to handle missing data. I realize the first one's not a true imputation. It's more of leveraging the design of a system and multiple observations to backfill in some probabilities. And the second one's a Bayesian-like model where you do predictive imputation. And both of these projects had lots of people who funded them. So these are the funders and collaborators for that PIT tag work. It was actually published and it's on Ecological Applications if you're curious about it, with Jody White, Kevin C., Andrew Murdoch, and Bryce Simmons being my collaborators on it. The Tuna work, we were advised by Grace Chu at VIMS, and then funded by a variety of agencies, but mostly the ICAT Atlantic Ocean Tropical Tuna Tagging Program. And my collaborators on that work are John Honig, Lisa Ayud, and Gulson De Silva. And it'll be coming out soon in Fisheries Research. And with that, I'd like to thank you and apologize for when PowerPoint decided to turn off. Apparently I was talking for too long according to my computer, but I'll take any questions.
Well, yeah, thank you, Dr. Waterhouse. That was great. Definitely appreciate the talk. For anybody who has any questions, we'll open it up now for anybody who's brave enough to unmute themselves and actually ask a question, Zoom face to Zoom face. Or if you prefer, you can place your questions in the chat and we'll go through those. I have a few of my own, but I'll maybe go to the question in the chat first. There's one from Alex. It says, thanks, Lynn. Question for you. Kind of new to Bayesian approaches. What is a good way to think about what a Bayesian model is doing when it imputes? How do you think about what imputation means and what's actually happening and how you know it's doing what it should be doing, which is, I think, a very good question.
That is a fantastic question. And I'm gonna throw up this slide just with a model for people who like numbers to look at. Ignore the equation if you don't like numbers and equations to look at. But so hold on, and let me switch this into presentation mode so it looks nicer. So in the germ model, we're trying to get at the number of missing rings, which is represented here by this X sub I. So what we mean by imputation is you don't actually know the X sub I, so it's NA. And so we're taking a data set where it's missing. We might have some values. So in the case where you're imputing part of your data, for some of your data, you have values here, which allows you to estimate these parameters. And so here, your parameters are the von Bertalanffy parameters, so the T naught, K, and D infinity. D sub 1I is the vascularized width of the spine, so that's an observation. So in this case, if you had some data where you knew the X sub I values, you would be using those values to calculate the three parameters from your model, T naught, K, and D infinity. And then you're going to use them with the observed vascularized widths to fill in the X sub I's that are NA. So that's where you're imputing them. So you're using a handful of data that you know to kind of predict the data that you're missing. So you can think of it as filling in or predicting. In the Bayesian sense, I like to think of it as predicting. Imputing, sometimes if you're just using the mean or the mode of similar datas, I think of that more as filling in. So the case where I've seen those examples given were more as if you had a temperature data set and you were missing, it's a daily temperature data set, you're missing 2 days of data, and you might fill them in by just averaging the 3 days before and the 3 days after to fill in those 2 data. So that's a simple example of imputation. But the Bayesian model, you'd come up with some mechanistic way to fill it in here. using a model that is based on the data you do have.
Cool. I think hopefully Alex got all that. Another time I might have you run through that again for me, but it's pretty cool. It looks like Dr. Feberg has a question, hand raised. Feel free to unmute.
Yeah, hi Lynn, thanks for a great talk. I'm just curious if you'd be willing to say something about software that you use or how you build your models, especially for those people that might be intrigued and want to do something similar, and also speak to, for example, the process by which you might fit your models and test them and make sure that they're working and things like that, like the work you did with the simulated data, if you're willing to speak to that a little bit.
Yeah. Okay. So I do all of my coding in R, and I learned Bayesian methods a while ago, so this dates me. So I do my Bayesian modeling in JAGs. Although in the case of so a newer one might be Stan, although Stan can't handle as many types of data as JAGs can. So these are the programs within R that you would use to apply your Bayesian model. Another one is Bugs. Bugs kind of was an older version. And then there was Julia is another one, I believe, that I've never used, but those are kind of the options I know of. Unless you're going to build your own, you can build your own. That's what like a true stats heavy person would do. But Stan has issues with count data. So for the germ model, it actually has to be done in JAGs. Stan would create a problem for it. So those are the models I use. And then the simulation framework. So this is, it's very useful in building a simulation to make sure that your model is doing what you think it's doing, but you also need to do it with the caveat in mind that any simulation framework you make and any simulated data you make are never going to be as good as real world data. And that's in no matter how much time we spend simulating data, real world data has more interesting error structures and patterns to it. So that's often really hard to capture. But how, so for the spine one, we simulated our data by first looking at a real world data example and coming up with, you know, what's the average spine size? What's the average vascularized size? Looking at some aged fish and building a model based on actual observations to make it mimic reality as much as possible, while acknowledging we're not going to mimic reality perfectly. And in fact, our simulated data is going to be too perfect. So that's always a problem. And then I always think it's important with your simulated data to make it messy. So we used uniform ages with a representative sample of every single age, which is probably not what you're going to get in the real world in fisheries. So I think it's also interesting to simulate a harder example, either by adding in more variability or making your sampling less. So don't cover all of your ages if you need ages to build the model, although you might, as we saw in the example of the skipjack data, by not having the old ages, you actually can't estimate a full von Bertalanffy growth curve. So you can have so little data that it doesn't work regardless of what you're doing. So you're trying to balance those two things between not having it be too perfect and matching a real world example. Sorry, I kind of talked on for a while there, but simulating data is one thing I like thinking about, and I think it's really useful to try to break your model and finding out at what points does it break, and thinking of it that way. And it can also have big impacts for how you do your field work. And I have some stories of how I've actually had to use simulations back in grad school to change how we did some field work collecting to avoid an issue.
Cool, thank you. Todd Arnold has his hand raised. If you want to go ahead and unmute.
Yeah, hi Lynn. I've seen cases of read studies where multiple independent observers will count growth rings for the same scale or otolith and come up with different answers. So there's a bit of maybe measurement error in the number of counted rings. And I wonder about the application of the kind of methodology you just described to dealing with measurement error, uncertainty in growth rings, or something of that nature.
I like your question. I hadn't thought of applying it to multiple readers counting growth rings. So usually people look at how well do users agree and come up with some type of score like that. Or this Tuna project that this data came from, they actually spent a lot of money, and their approach was a non-statistical one. They just spent more money training people and getting people in a room to come to agreement on the growth rings, deciding perhaps that was the better way to go to actually raise the expertise of everyone, and then hope that with a high level of expertise, your readings will agree more closely. But I haven't thought of applying this to actually getting a model for agreement of the users.
Great. Do we have any other questions? I'm looking in the chat. I don't see any other posted there, but I just want to give everyone a chance to ask a question directly by unmuting, or you can place it in the chat. If not, I might be more analogous to a naive model, so I have some questions, but I can go ahead with those while you think of yours. So just like a general question, you stated, I know there's just so many resources that go into salmon, in the Pacific Northwest, whether it be pit tagging, the hatcheries themselves, restocking hatcheries, everything but you said like 1.7 million were pit tagged last year or in 2020 or something like that. How many of those actually return? If you know offhand.
So I know, so the Steelhead numbers, it was like 400,000 were tagged. And then and that's beyond just Priest Rapids. And I only know the Priest Rapids number, and the Priest Rapids number is more like 13,000 being in the system. So there's lots of mortality happening at every stage, and then also human catch and consumption.
Yeah. And then I guess kind of going off that same matter, you were talking about these different arrays, a single array versus a double array, and in some of these different systems, do you run into issues if you're coupling an array with a weir, or like kind of integrating different sampling techniques within one system? Does that kind of convolute your data collection, or are you able to work within that and find ways to, could you potentially use a trap instead of a second array or something like that?
You could, yeah. So, which actually I should have specified to the passage estimates in that system with Tumwater, the place that we used actually as a checkpoint for was the model working. So that wasn't a simple array. That was one where they were looking at the fish and wanding them to get, or sending them through a chute with a reader in it. So you can combine multiple data sources. And if in fact you had more of a weir or more of a chute, and you were doing some double checking, you could actually, instead of letting the model estimate your detection probability, you could put it in as a hard coded number or put it in as a function of something. So another case when you might want to do that too is with those storm events and the water becoming too high for arrays to work, you can actually add in an equation for the detection probability to have it as a function of something like water level. So you could add in additional external information. It'll complicate your model even more, but the model can handle it, and it'll probably better represent what's happening if you have that data source.
Cool. I'll open it up for anyone else again, just here to see if anybody else wants to unmute. I guess I had just one other question on the spines, if no one else has any. Like I guess what percentage of fish have a vascularized spine, and like how can you, with those vascularized spines, can you couple that for validation with other like length and weight kind of curves and models and things like that to estimate an age? And that might be a naive question as well, but just one I was left with.
So it's actually, we're on the hunt right now for a data set that'll have paired otoliths with spines so that we can treat the otolith age as true ages and then use the spine data in a model. So it'll be one where it'll just be a model check using other sources of information. There are certain species too where you can actually use otolith weight is a good representation of age, in addition to the otolith ring count. And then the vascularization, for species where it just happens once the fish are older. And it also doesn't happen in this uniform way, I realized after seeing a few spine pictures. So sometimes, because it's not like a perfect circle growing outward from the center of the spine obscuring things, it's a weird, vascularized thing. So sometimes you can count more rings than you would think. So it's actually pretty variable too. And I imagine it would also vary by species as well. So I don't know how many of them have it as an issue. It's just, it becomes more problematic with older fish in the system.
Cool. Yeah, thank you. We're right at 12:58 right now, so I think we might we can give people 2 minutes to have some lunch or something. But I want to go ahead and just thank you very much, Dr. Waterhouse, for joining us today. It was a great presentation. If you do have any other questions or anything like that, I'm guessing Dr. Waterhouse would be open for you reaching out to her. And then for everyone else, we just want to remind you that we have another seminar next week, the same time, and we will look forward to seeing you there. So thank you very much for joining, and we'll catch you next week.